Alright, so in the last video we ended up with this setup and we wanted to, simplify it because this way it's a bit more obvious what we want to talk about next. And those are those weird spheres that develop over time. Even though in the beginning we have a nice stream, they then turn into spheres. So where is this coming from? Basically, it's almost a mathematical problem. Because what we have right now is that our spheres are generated, because we turn it off, with a velocity of 0. Because our sphere doesn't move in space, so our points will not have any velocity. And we can actually check this when we look into the geometry spreadsheet, which looks different for a DOPNet, because in our DOPNet there are much more things going on. So it wouldn't make sense to simply show the information about our points. We also have stuff like the gravity or the ground plane, or maybe some settings of the pop solver that are part of our world, so to say. So the geometry spreadsheet in a DOPNet shows much more than just the geometry. But if we want to have the geometry, we know where to find it, because our points live in the pop object. So there we open it. And here we find information about, for example, what kind of forces are applied to those points, which is the gravity, for example. And here there is geometry, and this is what we're looking for. And then we have back our classical geometry spreadsheet, where we will find all the attributes that are used inside of our simulation as well. And there are actually a lot of different attributes that are created by our simulation. We'll talk about some of them later on, but what we care about right now is the velocity, and the attribute name for a velocity is v. And what I wanted to show you here is that you can always read out what the information or what the properties of a point are. As you can see in the first frame, they are 0. Now what happens if I press start? You can see they accelerate downwards, of course, because they're falling. And one thing that is important, as you might remember from physics in school, a gravity force is an acceleration. Any force, in fact, is an acceleration, and the gravity node accelerates downwards by 9.81 meters per second, as we've learned once maybe. And this is what's happening here. Our velocity is accelerating downwards. So that's the first thing. It's not a constant velocity, but it's accelerated. Now that still doesn't explain why we have spheres here. Well, partly it is because if you have points that are generated around a sphere on the surface with no velocity at all, and all of them will be accelerated by the exact same speed downwards, then you will end up with points that move in the exact same speed next to each other. And the reason the sphere gets more visible over time is simply that they go faster and faster and faster and faster. And part of the problem here is that we currently only calculate a new position for each of the points every full frame. And this is simply the result of all this. If you take a couple of points around a sphere with the exact same speed, with the exact same acceleration over the same amount of time, and you only do this once per frame, then this is what you get out of it. Now, how do we solve this? Because obviously that's very unnatural. The first and worst solution for this is to simply increase the amount of times we calculate the sphere. So let's start with this, even though I don't think it's actually a good solution here. How do we do this? We can tell the simulation to calculate more than once per frame, and we have multiple ways of doing this actually. We can do this directly in the pop solver, so the brain of our simulation, and here you can find on the first tab the sub-steps. But there's another way of doing it, and that is not just for the brain in our simulation, but for the whole PopNet, so the whole world, so to say. Now, it's not completely the same, because the whole world will mean that all the nodes in here will be calculated multiple times per frame as well. But in our case, it doesn't really make a difference. Later on, we will see cases where it does make a difference. Now, if you're not sure where to save it, my best bet is always to change it actually on the PopNet. So change the amount of calculations for the whole world, so to say, by selecting the PopNet, going to simulation, and there it is, sub-steps. So let's set this to 3, let's say, and let's run this. And when we go a bit more at the beginning, we can see it now seems much better. It seems to be gone. Well, actually, it is not gone. It's just less visible. If we go further down, sooner or later, it will come back, the problem. It's just that in the beginning, there are so many steps, basically, that we don't see the single spheres anymore. There's another downside of this technique, and that is, of course, when we set our substeps to 3, all the calculations that happened before now have to happen 3 times more often. So the whole thing gets 3 times slower. Now in this case, it doesn't really matter because the whole simulation is already so fast that it doesn't make a difference. But you can imagine later on when we do this with much bigger simulations, this is not a good solution because it doesn't really solve the problem, it just hides it. And on top, it actually makes our whole simulation slower. What's the better solution? Let's set this back to 1. And keep in mind, this is so inherent in every simulation that you will see this in the rest of the course all the time. It's a common problem that we have to solve in the world of simulations. And the better solution than increasing the sub-steps, even though there are some cases where you can't go around that, is to actually make sure that simply our points will not come to the same conclusions every frame with all the other points. Now we can't change the gravity for this. Gravity is always the same for all of us, but what we can change in reality is when there's something coming out of something, it's very unlikely that all the points have the same start speed of 0 like here. So as we've seen, we already have a solution for this. We can simply make sure, let's set the main velocity to 0, but let's add just a little bit of variance to our start velocity of 0. And now you can see here on the first frame that our velocities already have random velocities. When we press start now, this results in a more broken up result for each point. And in this case, when we do this a bit stronger for y, maybe with a variance of 1, you can see that the problem is basically gone because every single point now starts with a different start velocity and will therefore end up with a different result after each frame. So the trick basically is add some variance to your simulation. However you do that, it depends on the context, of course. And this is why you will always find a variance in most of the settings that we can control in Houdini. And the next thing though is, you see me here fly around my simulation and look at it from all kinds of angles, but in reality that's actually not how we work with those simulations. Because in the world of VFX and animation at least, we will always have a certain camera that looks at an effect. And we actually have this camera before we start the effect. I know as a beginner, as a hobbyist, and as a student, you usually create the effect and then you decide the camera afterwards. When you do this as a job, it's actually the other way around. You always have the camera first. And let's mimic that by quickly creating our render camera. So I don't know, something like this. And let's actually call this render cam. And the reason I'm telling you this is everything that matters to us is what is visible in this camera. Nothing else is important. But as you have seen now, the problem is when we let this run for a while, there's actually a lot more that we have to simulate. And that is all those points that fly further down into the abyss. All those points have to be calculated by our computer without us actually caring about it at all. And this is very important. Make sure that you optimize your setups so that you don't have to calculate unnecessary things. Again, in this case, it doesn't matter, but later on it will. So how can we do this? For this case, in terms of particles, there's actually a very simple solution for this, because under birth, where we set the amount of particles that are generated, we also have another very important thing, and that is the life expectancy. So each point in our simulation has the questionable privilege of already knowing when it will die. Because what the 100 means here is that every point will die after 100, not frames, but again seconds. And 100 seconds basically means infinity in the world of VFX and animation, because it's extremely unlikely that you have a shot that is that long. Let's lower this to something that makes a bit more sense, maybe to 2 seconds, and then let's have a look what's happening. And if you go out, we can see at some point, there you go, the points die. Let's actually go a bit sooner, maybe 1 second. There you go. And the thing is, currently it fizzles out okay, and that is because each point had a different start velocity. But let's set this back under attributes to 0, because I want to show you something. If you wouldn't have set the start velocity like we did, you would see that the sphere, that the particles in form of our sphere here will die exactly at the same time. So they suddenly all just disappear. Now, here again, it's a good idea to add a variance, which actually is the next parameter next to the life expectancy. And just like we saw before, when we add a number here, let's say half a second, then it will be added and subtracted from the main life expectancy. Meaning the earliest point will die after half a second, the latest point will die after 1.5 seconds. And then it looks like this. If we rewind, it fizzles out a bit more like this. Now let's combine this again with our start velocity, and the whole thing feels pretty smooth. Even though, yes, in our case, we will never see that because our render cam only showed this part here. So in our case, we would just make sure that the life expectancy around here kills the points. So I think 1 second is fine, so that all those points that before had to be calculated will not have to be calculated anymore because they simply die. Now, as a small side note, things like life expectancy will actually also be saved in form of attributes. So later on we will see we can actually override that. So let's type in life here, and you can see every point has an attribute that tells them when it will die. We'll talk about this later. Just as a side note, the general rules that we learned, that everything in Houdini is based on attributes, is not changing in the world of simulations. Everything in simulations is based on them too. All right, let's finish by bringing back our original movement, maybe something like this, 4-4, with a little bit of spread in X and Y, and then we add our ground plane again. Oh, the life expectancy is now a bit too low, maybe set it to 3 or something. And now we can see we have here our rainbow cannon that doesn't have the strobing effect anymore because we took care of this by changing the variance. We steal the colors from the sphere because every attribute by default, because this is what the star here means, will be inherited from the geometry that we scatter on. On top of the spread, we actually also gave our points a start velocity so that we have a nice stream here, and we added a ground plane and of course gravity to make the whole behavior, make a bit more sense and be a bit more interesting. If we wanted to have more or less points, we find this under birth. Usually we use constant birth rate, which is per second, but we could also do it with an impulse count, which is per frame. There is no right or wrong here. It purely depends on what makes more sense in the effect that you're working on. And then at some point our points will die because they actually have a life expectancy built in that can be helpful to limit the amount of points that you have to calculate, especially when you don't see them anymore in your camera. For example, like here, when we only see this of our effect. So as you can see, there are a lot of things that you need to understand and have to deal with, even when looking at a simple setup like that. So play around with all this, and in the next couple of videos, we go further into what we can do with all this, especially when it comes to collisions with other objects. So for now, I hope this is helpful. Thanks very much and see you later. Cheers.